Hello, everyone. Glad you could join us today. As Kevin was mentioning, the topic is hydraulic testing of existing hydronic circuits. And this is, if you will, a part two or a follow up to the June Modern Hydronics and Heat Pump webinar. And if you missed that, that was on thermal testing of existing hydronic circuits. How can we determine the heat output of an existing circuit at a given supply water temperature? And if you did miss that, there's a link here, or as Kevin was saying, go to the Enertech YouTube page, and it was the June 2025 topic. You'll see it right there at the top of the list. And I'd encourage you to look at that because we did talk about a test apparatus up here in the upper right of your screen. You can see we've got an ultrasonic flow meter and a dual channel temperature meter. We use those to do the thermal testing, and we're actually going to use the ultrasonic meter for the hydraulic testing as well. Now, again, last month we talked about thermal testing, so I'm just starting here with an image of just a real basic circuit. It's piping, it's a circulator, there's some type of heat emitters in that circuit. It could be a residential, could be a commercial circuit, but it's a single circuit. It has some type of heat source that supplies heat to the circuit, and we want to characterize that circuit. And one of the analogies that I'm going to give you when we talk about hydraulic characterizing a circuit, imagine you're designing an airplane. And one of the things that is done with airplane design is to sometimes put a scale model of an airplane in a wind tunnel and blow air past it at different speeds and actually measure the drag that is occurring because of the friction of the air moving over the airframe. And by doing that, you're characterizing the aerodynamics of that airframe, and you can use that information along with the power of a given engine. Let's say we want to consider a 100 horsepower engine or a 300 horsepower engine. How fast will that airplane go with a given horsepower providing the thrust? So the hydraulic analogy of this is if we have a given circulator in there and we have a certain flow rate and we characterize the circuit, you might ask a question, what would happen if we put a bigger circulator, or for that matter, a smaller circulator, or even what would happen if we changed the speed setting on the circulator? If we go to a higher speed, intuitively, we know we're going to get more flow in the same amount of time, a higher gallon per minute. But how much more? Is it worth running the circulator at the higher speed? Is it worth going to a higher performance circulator? And these are questions that would come up not only in the context of adding a heat pump to this system, be it air to water, water to water, geothermal, but in general, if you're adding a heat source, a good example would be, let's say we're replacing a cast iron boiler with a wall hung boiler. That wall hung boiler is going to have a very different drag characteristic or head loss characteristic. And we would need to factor that in when we determine is the existing circulator big enough to handle that, or do we need to go to a larger circulator? So there are very practical questions that can be addressed and addressed using numbers rather than just guesstimating by characterizing these circuits. Now, in last month's webinar, we talked about this test apparatus here, and I'm just going to give you a quick review. Basically, we're going to tap into the circuit where the existing circulator is. And typically today we find either isolation flanges like I'm showing here, or ball valves that are on either side of the circulator flange. So it's possible to close those flanges or close those ball valves, remove 4 bolts, and just slide the existing circulator out. So this is the easy way to tap into the circuit rather than cut the pipe and try to temporarily create some type of apparatus and then have to go back and repair it. So we're going to use a couple flanges, and they're going to have what are called baseboard tees. And these are just typically 3/4 inch elbows that have a little side tapping on them. I'll show you a zoomed in view here in a minute. That little side tapping is an 1/8 inch female pipe thread, and we can tap into that with a tube or a valve or some type of instrument. Down below, we've got our ultrasonic flow meter. Last month, we talked about these. Keyence was the name of the manufacturer that I referenced. These are available. You can buy them directly through Keyence dealers, or you can find them actually on eBay at a pretty good price. Typically, I'll say a price point in the range of maybe $400. Very reasonable price for an instrument. If you think about other instruments that you typically use, like combustion analyzers or other types of quality meters. And that basically mounts directly to the outside of the pipe. You do not have to cut the pipe or pierce the pipe in any way. And using sound, high frequency sound, it can determine the flow rate. And we also are using this dual channel temperature meter. These are just thermocouples that would be taped onto the pipe. And we use those to get the temperature rise from the return to the supply side of the circuit. And that was part of that thermal testing procedure. The rest of this apparatus, there is a variable speed pump down here. This would be one of the new ECM circulators. If you're thinking specific products like a Grundfos Alpha circulator or a Taco 007E would be another one. Something where we can adjust the speed of the circulator. And our temporary heat source was a block heater. This is just a device that is used in vehicles, typically in diesel engines, when it's very cold, to pre-warm the coolant in the engine before attempting to start the engine when it's really cold out. And they're available online. They're not very expensive. They're $75, $80. It's basically just a little can that has a 1500 watt heating element in it. And you would connect that up to the piping downstream of the circulator, and then a piece of hose back up here. And then over on the left here, we have a inexpensive watt meter. It's actually, the brand is Kill-A-Watt. They're about $30. You can find them online. They're accurate enough for this type of testing. And we just run a line cord from the heating element on the block heater over to this. So we can measure the actual power going into that heater, and knowing that and the flow rate and the temperature increase across the test apparatus, we thermally characterize the circuit. Okay. And again, I don't want to spend too much time on that other than refer you back to the June YouTube to get a much more detailed explanation of that. So what we're going to do with hydraulic characterizing is we basically want to come up with what is the head loss of the circuit at different flow rates. What is head? Head is mechanical energy that's imparted to the fluid by a circulator. You can't see it. You can't taste it. It's basically the only evidence that head energy has been injected into the fluid in the circuit is an increase in pressure. When we use a circulator to add head to a fluid, the pressure on the discharge of the circulator is higher than the pressure on the inlet of the circulator. And we're going to use that relationship between the pressure change across the circulator, and we can convert that back into head. And we're going to do that at different flow rates. Now, we're going to zoom in on this upper portion of this test apparatus just so you can see it a little bit better. So again, here are a couple flanges. These are bronze flanges that you can buy from different manufacturers. And being bronze, you can either silver solder, braze, or perhaps even solder a short little stub of copper tubing in there. And then this is a baseboard T. It's basically a 90-degree elbow. You can buy these in 1/2 inch, 3/4 inch, 1 inch, and they all have a little 1/8 inch tapping. The reason they're called baseboard Ts, they're often installed on baseboards in a hydronic circuit, and often the baseboards are the high points of the circuit. And typically they have a little manual air vent screwed into that 1/8 inch FPT thread port. And they're just there so you can bleed some air out of the baseboards. But anything that has an 1/8 inch male thread will thread into that. And you can buy little ball valves that actually are 1/8 inch, just like male on one side, female pipe threads on the other. Again, just literally, you could go to Amazon, you can go to eBay and type in what you're looking for, and you'll find sources for these. The next fitting up here, this is an 1/8 inch male pipe thread by barbed adapter, and it converts over to 1/8 inch barbed tubing. So basically, just like any barb fitting, it will accept a piece of tube, and typically 1/8 inch fuel line works fine. You can slide the 1/8 inch fuel line right over that barb. Of course, this would be threaded into the valve, and then just use some type of a little ratchet clamp, the little plastic ratchet clamps, or you could use a stainless steel clamp of some sort, anything that will clamp that hose onto that barb fitting. We're not going to go to really high pressures here, but something that could withstand, I would say, at least up to 30 psi. And then we're going to use the same type of fitting along with a T up here, coming in from both sides here. Both sides are identical. So these two adapters go into this 1/8 inch brass T or stainless steel T. And we're going to tap a pressure gauge into that. And we'll talk about that pressure gauge in a minute. So what is this whole assembly? Why do we create this thing? Well, if we have both of these valves open, essentially this gauge is going to read the static pressure in the system. Let's say the circulator is off and we just open this ball valve and this ball valve. We're going to get the static pressure in the circuit. That could be 10 psi, 15, maybe even 20 psi. That's just the pressure that's resident in that circuit because you've got an expansion tank and you've pushed fluid in against the diaphragm of that expansion tank. So in a sense, the expansion tank is like spring loading the circuit. You've got this pressure. So that's, static pressure. Now, if you open one of these valves at a time, you're going to actually get what's called the dynamic pressure at that valve location. That would be the static pressure plus the pressure created by the circulator. That's what we call dynamic pressure, or sometimes you'll hear it called total pressure. So the pressure gauge on the discharge side of that circulator, when you open that valve, that pressure is going to go up because we're adding head energy to the fluid, which means our pressure goes up. So we're going to get the discharge pressure at this point, and then we're going to close that valve, open the other valve, and we're going to get the pressure on the inlet side of the circulator, or I'll call it the return side of the circuit. And now we have two pressure readings, one on the supply side of the circuit, the other on the return side of the circuit. We can easily subtract the return side pressure from the supply side pressure, and that's what we call delta P, or the pressure differential. So at that point, we will know a pressure differential, and we will have that ultrasonic meter back over here that's actually giving us the flow rate that corresponds to that pressure differential. And we're going to do that for several different flow rates, and then I'll show you how to organize that data and come up with what we call a circuit head loss curve. Okay. And again, why are we doing this? So once we characterize that existing circuit, we can then evaluate what would be the effect of changing the circulator. Maybe we have a circuit that is maybe the last baseboard on a circuit is cooler than we want because the flow rate's too low. Maybe somebody created a really long circuit, or maybe there's something in the circuit that has impaired the flow rate, some kind of scaling or some other effect. And we've decided, gee, we want to get more heat out of that last baseboard on that circuit, so let's increase the flow rate. All right, so we're going to do that with a bigger pump. How much bigger pump? Well, this procedure will let you come up with a justified answer for that question. Okay. Now, selecting this pressure gauge. Remember, when both of these ball valves are open, excuse me, we're going to be reading static pressure. And typical static pressures in residential systems that, these are low-rise residential systems, maybe single-story or two-story house. Commonly, they'll run in this range of 10 to 15 psi. They don't have to be. They might be a little lower than that. They could be a little bit higher. But most residential, light commercial systems actually have 30 psi rated relief valves. So you really don't want to get to 30 psi or even 29 psi because you're getting close to the point where the relief valve would start to open up. But in any case, we're going to have a static pressure. So, if, for example, let's say the static pressure was 15 psi, and if we put a pressure gauge in that only goes from 0 to 10 psi, we're going to spike the needle right to the end of the gauge. And, the needle like to go farther, but it can't. So we have to have some idea what the static pressure is. And typically there is a pressure gauge in most hydronic systems. Sometimes it's part of the gauge on the boiler or a separate gauge. Or if you have a boiler drain in the system and you don't have any other gauge, you can just rig up a little assembly where you could use a hose threaded adapter, screw it onto the hose bib, and just adapt it over to a pressure gauge, like a 0 to 30 gauge, and just open the valve and you'll get the static pressure at that location in the circuit. Now, typical circulators, they will add anywhere from 0 to 18 psi when they operate. 0 would be, kind of impractical, but 18 psi, that would be actually a pretty high head circulator. That's probably a circulator running in a range of 250 to 300 watts. A more typical pressure increased across a residential circulator, something like a Grundfos Alpha or a Takeo 007, probably in the range of 4 to maybe 8 psi. Okay, so if we take these into account, and this is a rough relationship between psi and feet of head. I'm going to show you a more accurate way to actually make that conversion factor there. But I just threw a couple examples up here of pressure gauges. The one on the left there, this is 0 to 15 psi. It's a nice quality gauge. If you had a system with a static pressure of, let's say, 5 psi, and you've got something like a Takeo 007 circulator that might add another maybe 7 psi, 5 plus 7, 12 psi when the circulator is running, this gauge would be fine. On the other hand, if you had a circuit that had a 15 psi static, and then you're going to put a circulator in it and add another, let's say another 10 psi, well, that would be 25 psi. So we would need, in this case, a 0 to 30 psi. And of course, you could change these around. They would be typically 1/8 inch male pipe thread, or I'm sorry, typically they're going to be 1/4 inch male pipe thread. So you may have to get an adapter to tap it in over here, but basically you're going to connect that thread on that pressure gauge to that teep, either directly with 1/8 inch or with an adapter coupling to bring it over to 1/4 inch. Okay. Now let's talk about the procedure itself. We'll start once we've got this apparatus in place. And by the way, this is part of the same apparatus we talked about last month. So it isn't necessarily something you have to build in addition to what we talked about last month. We just didn't use it last month. But let's say the apparatus is in place. We're going to close both valves. We're going to turn on the variable circulator. Now, that's the circulator that's down here in the apparatus. Remember, we've removed the circulator that existed in the circuit, and we're going to power flow through the circuit using this variable speed circulator. And let's say we adjust its speed, and many of them have either buttons or a dial where you can vary the speed of the circulator. And let's say we start at a relatively low flow rate in the range of 1 to 2 GPM. It does not have to be exactly 1 or exactly 2, but something in that range. Basically, just turn up the dial on the circulator, wait till you get some indication on the flow meter that you got a relatively low but stable flow rate. All right, so now we have flow going through the circuit. We're going to open the ball valve on the supply side over here. This one's still closed. This one's open. So now we're going to get the dynamic pressure at this point on that pressure gauge. Okay. And we're going to record that. We'll just write it down. All right. Next step, close this one off, open this one up. Now we're going to get the dynamic pressure on the return side of the circuit. So we're getting two separate pressures and we're going to subtract the lower one from the higher one. And that's what we call our delta P, or pressure differential. Okay. So let's say our first test flow rate, and I just picked these numbers arbitrarily. Let's say our first one was 3 gallons per minute, and we measured a pressure differential. Again, that's the subtraction of this side pressure from this side pressure of 0.7 psi. All right. Next step, just boost the speed on the circulator, turn the dial up, go to a somewhat higher flow rate. I'm showing here 6 data points. That's plenty. Is there any advantage in getting 10 data points? Not really. For the precision that we're working with here, you don't really need to have a lot of data. You definitely want to have, I'd say, an absolute minimum of 3 data points, preferably going 4 or 5. But honestly, this procedure is fast. It literally within a minute, within 30 seconds, you can change those valves, record those 2 pressures, and move on to a different flow rate. So it's not as if this is taking a lot of time. So basically, we just keep repeating steps 3, 4, and 5. And you can see here, we're just going to higher flow rates. And each time we're recording 2 pressures. And actually, you could make another column in the spreadsheet, what the supply side pressure is, what the return side pressure is, and then just do the subtraction. I'm just showing the results of the subtraction. And you'll see another column over here that's labeled head loss. And I'm going to show you how to get from differential pressure over to head loss. Okay. Let's keep going. It says measure the supply and return temperatures on the circuit and average them. Now, you might say, why do I need these temperatures? It's because we have to characterize the density of the fluid that we're working with. It could be water, or it could be a mixture of water and antifreeze, but we have to know what the density of that fluid is at the condition that we're testing at. And that is part of converting from differential pressure over to head. So again, if you've got your dual temperature unit, just take a temperature reading on supply side, take one on return side, and average them. If you don't have a heat source operating, all you need is to put a thermocouple on the pipe, get a temperature. And then here's a graph. And again, the PDF that'll come out after the webinar here will have this graph on it. And what this is, it's a plot of the density of 3 different fluids as a function of temperature. And you could see for water, as you know, as water gets hot, it expands and its density goes down. And this just gives you a number. So at 140 degrees, we could go up here and read maybe about 61.4 pounds per cubic foot for density. You can see the density of 30% propylene glycol or 50% propylene glycol. Not only is it higher than the density of water, but it's also strongly dependent on the temperature that we're working at. Okay. So that measurement of temperature is, then you go over to the graph, read up. Again, you're going to have to know the fluid that is in that circuit. If you think it's antifreeze or you open a valve, but you're not sure what concentration, you can get yourself what's called a refractometer. They're inexpensive meters. You put a few drops of the fluid in, and basically you look into a prism on that, and it'll give you a rough idea of what the concentration is of that fluid. Okay. Now, we've been measuring and recording differential pressures, but what we need to get the proper units to evaluate a new circulator, we need to convert that differential pressure into head. And here's the formula. It's a simple arithmetic formula. So for each differential pressure reading that we took, we're going to multiply that by 144, and then we're going to divide by the density of the fluid that we read off of this chart. Okay, now you might be thinking, I thought head was just delta P divided by 2.31, or delta P times 0.43. That's an approximation. It's based on water. It's based on water at room temperature. Depending on when you take these measurements, if that circuit is hot and if the circuit has a fluid other than water in it, that rough approximation, it has error in it. So this is a more accurate way to convert from a differential pressure reading over to a head. And it's not hard. You measure the temperature of the circuit, you go to a chart knowing the fluid that's in the circuit, you look up the density, and you just run it through your calculator. Okay. So now I've completed the third column on that spreadsheet. This is the same data that we were collecting before. So we had a given flow rate and the associated differential pressure measurement. And then as we went up in flow rate, you can see our differential pressure goes up. And over here in red, I'm just using this formula to convert those differential pressures over to head. And I forgot what temperature I based this on, probably like a room temperature. So now I have a head at each flow rate. Okay. Now we're ready to actually make a graph that characterizes that circuit. And here it is. It's nothing more than a graph. On the horizontal axis, we're graphing flow rate. And on the vertical axis, we're graphing head. And think of this, this is the head loss of the circuit. And this is a very typical relationship where you've got this curve. The curve gets steeper as you go to higher flow rates. And typically, well, always, if it's a closed hydronic circuit, fluid-filled circuit, at zero flow rate, you have zero head loss. Head loss is the result of friction in the fluid. If the fluid isn't moving, we don't have a frictional loss effect. So one point is always going to be 0, 0. And then, for example, here was our first flow rate at 3 GPM. We had 1.6 feet of head loss. So at 3 GPM, it's 1.6. And then again, I just put these numbers into any spreadsheet program. Or if you want to, you could take out a sheet of graph paper. I mean, I'm an old school engineer. I still remember how to use graph paper. And you could plot this out on a graph. And then you would basically just draw a nice smooth curve up through there. Okay. And that is what's called the circuit head loss curve. And the analogy I'll use for this, I like to use the analogy of a fingerprint. Just like every individual has a unique fingerprint, every hydronic circuit has a unique circuit head loss curve. It depends on the pipe size, the amount of pipe, the amount of fittings, the components like air separators, valves, heat exchangers, heat pumps, boilers. Whatever that fluid is going through will have an effect on that circuit head loss curve. So imagine any kind of circuit you want, there's always going to be a head loss curve. And basically, that's what we just measured. The data we took allowed us to create this graph. Okay. Now, notice the graph says head loss. This is the loss of mechanical energy due to friction as the fluid has flowed through the circuit as a function of the flow rate. All right. So that's head loss. The next step is to put another curve on the same graph. And that red curve is what's called the pump curve for a circulator. And I'll show you an example, but you can go to any website or pick up any piece of literature for circulators. And one of the things you'll find is a pump curve. And the pump curve is the head added by the circulator at a given flow rate. So for example, at 0 flow rate, this particular circulator adds about 20 feet of head. Okay. At 2 gallons per minute flowing through the circulator, it's capable of adding, looks like about 18 feet of head. At 10 gallons a minute, it's capable of adding about, looks like about 7 feet of head. So this is head energy being injected into the circuit by the circulator. This is head dissipation or head loss due to friction. And you can probably guess what I'm going to say next. Where those curves cross right here at this yellow dot, This is where the head added equals the head being dissipated. This is called the operating point. Or sometimes I use the term hydraulic equilibrium. This is where the mechanical energy being injected into the fluid by the circulator is exactly balanced by the head energy being dissipated by the friction as that fluid goes around the circuit. And that's where the circuit wants to operate. I use the words here wants to in quotes. If you think of it as as a being or an entity or something that has some intelligence to it, this is where things will settle in. And in this case, if we just drop a line straight down, it looks like about 8.5 gallons per minute is where this particular head loss curve representing a particular circuit combined with this particular pump curve, again, representing a specific circulator, this is the flow rate that we're going to get. So, we don't have to guess that, gee, should we use a 007 or should I use a 009 or should I use a Grundfos 1558 or a 2699? There's no need to guess. We now have quantified it. We've got a picture that will tell us what we're going to get. And the next slide here, this is typical of the literature that you would find, or if you go to their website, you'll find a family of pump curves. This happens to be for Grundfos, and here's all the different model numbers, okay, for these pumps. And each model number has it has another number assigned to it on the curve. So, for example, curve 1, UPS 26116, it's a pretty high pump curve, okay? But if that red curve represented the circuit head loss curve, I know if I put that circulator in, it's going to cross right here where I'm moving this little laser pointer around. So if I drop straight down, I'm somewhere around 22 gallons per minute. Now, if I pick a really small circulator, number 7, that would be a UP 1510. That's probably more like a domestic water recirc pump or circulator. The crossing point's right here, so I'm a little over 6 gallons per minute. So yes, when you put a bigger circulator, a more powerful circulator in the same circuit, you're going to get a higher flow rate. But I've watched people try to guess at this. If it's twice the wattage in the circulator, do I get twice the flow rate? No, that you can't make generalizations like that or assumptions like that. So this is a way to do it correctly. Just an example, here's the yellow dot where the higher pump curve here, the UP 26116, represented by pump curve 1. So we're right at about, if we drop that line down, we're at about 22.5 gallons per minute. Okay, same circuit. If we go to let's see, number 6 is a UP 1542 circulator. There's the crossing point. We drop the line down, 12.5 gallons per minute. So, this is what I would call Hydronics 101. Whether you're working with heat pumps or boilers or any other type of hydronic system, knowing how to quantify the characteristics of a hydronic circuit and then match them up or combine them with the hydraulic characteristics of a circulator, that's really important in hydronics. And again, there's no need to guess and say, gee, it's a small house, I use a small circulator. It's a big house, I use a big circulator. Don't do that. These are techniques that are readily available. The information's available. The testing procedure we've described is pretty easy to do. If you don't want to make graphs, we do have software. And I've worked with another engineer for many years. We've have a product called the Hydronics Design Studio. Right now, we have the current version, version 2.0. But just a little advance notice, next quarter, we'll be releasing version 3.0, the Hydronics Design Studio. And it can do all this number crunching without making any graphs. All that mathematics is taking place behind the screen, so to speak. And you can create circuits with multiple branches. You can pick a circulator from a list You could tell it the pipe size. You could tell it the fluid temperature. You could select the fluid that's in the circuit. And this will literally simulate what would happen if you create this circuit and put this circulator in it. And you can do all the what ifs. What if I add another branch? What if I change a pipe size? What if I go to 40% propylene glycol versus 20%? And literally, by the time your finger comes off the key, you've got the answer in terms of the flow rate, the head being added, individual branched flow rates. You can turn balancing valves on and off. There's a lot of things you can do. These are all the different modules that are in the software. You just click on them and you'll get a different screen. Again, there's a free demo version of this right now. If you want to go to our website, hydronicpros.com, you can download version 2 demo, take a look at it. We will have a very good upgrade opportunity to go if you have version 2 and you want to go to version 3. It'll be done at a very minimal cost. So just I'm throwing it out there just to give you an idea that, gee, I don't like to make graphs and so forth. Use the computer to find this kind of information. You still are going to have to characterize a circuit, though. You're going to have to know, for example, does the circuit have 150 feet of 3/4 inch copper pipe? Does it have 20 elbows? You know, the measurement procedure that we've talked about today is unique because it picks up all the nuances of the circuit. For example, somebody might have put a valve somewhere in that circuit, and for whatever reason, they left the valve half open. Maybe the valve's way off in a crawl space somewhere, you don't even see it. Well, when you test that circuit, the influence of that partially open valve is going to show up. But if you're using the software, it can only do a theoretical analysis. If you know exactly the parts and pieces that are in that circuit, yes, it can build a pretty accurate theoretical model, but it wouldn't pick up on the fact that, gee, there's a valve I didn't see that's half open, or for whatever reason, I've got sludge in the system. I've got, I've got a kink in a pipe somewheres that is causing some kind of a flow restriction. These are all things that would be picked up by physically testing the circuit, but not necessarily picked up in a software simulation of that same circuit. Okay. So that's it. As far as the presentation, I'm going to go back to Kevin. I know we have some questions that have come in, and feel free if you've got questions about the subject, we'll try to address them in what time. We got about 20 minutes left here.
Yeah, we still got about 20 minutes. So if you guys have any additional questions, go ahead and post them now. I do have some here for you, though, John, and I'll ask one that just was posed during that last slide just to provide clarification. It says, will version 3.0 be available for iOS devices? You might as well touch on Android as well.
We do get that question quite a bit. No, this is created for Windows. Now, I use a Mac. Many people use a Mac. It is something that you can run on a Mac using Parallels desktop software. You're basically emulating the Windows environment on a Mac. So yes, I do run this on a Mac using Parallels desktop, but there is no Mac native version, and it is not something that runs on a phone. You don't, or an iPad for that matter. The screens are pretty detailed. If you look at, this is only part of the screen. I mean, there's other branches we could turn on over here. So ideally, you're running it on Windows. It will run on the latest version of Windows. It'll run backwards compatible. We're actually going through testing on that right now. So, but there is no native Apple version of this.
Okay. I've got one that I wanted to touch base on that was pre-submitted. It's pump sizing for unknown circuit lengths for retrofits.
Mm-hmm. Well, this procedure is exactly what you need. Unknown circuit length. Okay, so we don't know the circuit. If you can get access to where the circulator is, build this test apparatus, put it in there, and just go through that procedure, you can create the circuit head loss curve for that circuit. You don't even have to see the whole circuit. Okay. You create that curve and then you can match it up with a pump curve, and that will give you a pretty accurate estimate of what the flow rate that circulator will do for you. So yeah, perfect application for this test procedure.
Okay, thank you. How many different flow rates does the circuit needed to be tested at? Does the circuit need to be tested at?
I would say anywhere from 4 to 6 to 7. I don't think it's worth going to 10. I mean, you can always create more data points. Um, but if I go back to that picture, let me just back up here a minute. So we've got this point is always a given for a closed fluid filled circuit. You're always going to have zero head loss at zero flow rate. So that, in a sense, that's a given point or an intrinsic point. 1, 2, 3, 4, 5, 6. That's plenty. And you can see, even before you draw the blue line, you can see the trending. So literally, if you just draw connect the dot type of things, you'll get enough accuracy to make this intersection with the pump curve, and you can estimate the flow rate in probably to the nearest tenth of GPM. Now, I will point out something. Manufacturers publish a pump curve. I've talked to manufacturers about this, and the general idea is that the pump should be within plus or minus 5% of the published pump curve. Obviously, if you're producing, if you pick a number, 1,000 pumps a day, they're going to be all pretty close, but they're not all going to be absolutely identical. And yet they're going to have the same pump curve in the literature or on the website. So remember, this is not, this is not something where we're generally trying to pin that flow rate down, even to a tenth of a gallon per minute. If the flow rate in this circuit instead of 8.5 was 8.7 or 8.4, 8.3, imperceptible difference in terms of actual thermal output at that variation. Now, if we estimate 8.5 and for whatever reason the circuit operated at 4, yeah, that would definitely make a difference. But within the precision and the accuracy that we're trying to create here, I would say anywhere from 4 to 6 data points is fine for the graph.
Okay, thank you, John. Let's see. What if the circuit is operating with an antifreeze solution rather than water?
Okay. There's the graph. What you're going to need to do is determine what antifreeze concentration you have. Now, I plotted out curves here for propylene glycol. It's possible you might have ethylene glycol in the circuit, and that would be slightly different density. All I did to make these curves is go to the website for, this is based on Dow Frost, and Dow Frost is from Dow Chemical. It's a inhibited propylene glycol antifreeze. You could go to any manufacturer's website and you can find the data for density of a specific fluid, meaning is it Dow brand, is it brand X and Y, at different concentrations and at different temperatures, and just plot that curve out. But we do have to know the fluid in terms of if it's propylene glycol versus water, and what the concentration is. Again, if you're not sure on the concentration, there's a couple of things you can do. The easy one is to buy yourself a refractometer that can tell you the density or tell you the concentration of that fluid. You can also take a sample and send it out. For example, Dow has a lab. Some of the other manufacturers have labs. They can test it and tell you, but that means you got to send a sample out and get it tested. A refractometer, honestly, $25, $30 is all you need to get an estimate. And somebody might say, well, what if it's 40% propylene glycol? We'll just interpolate between these curves. Basically imagine a curve that goes halfway up between these two curves. So that information, even if you don't want to use this graph, you can, if you know the fluid, it's, brand X at 45% concentration, you can go to the website and it'll look that up. In fact, I'm just thinking you probably could ask AI to go out and find that information for you today. And or what is it, Chat GPT? If you ask Chat GPT, what's the density of a 45% solution of Dow frost? It probably could go out and find that information for you.
Sad but true. These questions are kind of similar, at least they piggyback off one another, so I'll kind of tell you both of them. Do I need to know the temperature of the fluid during the test? And does the fluid need to be heated to a specific temperature to do the test?
Good questions. Yes, you do need to know the fluid temperature because whether you're using this graph or using manufacturer's data, you can see, for example, if you were testing at 180 degrees and you had a 30% glycol, you'd be at around little under 62 pounds per cubic foot. But if you're testing in a basement at, say, 60 degrees, you'd be upwards of 65 and a half. That is going to make a difference in this calculation. So, yeah, you need to know the approximate temperature of the, again, plus or minus 5 degrees is not going to make much difference. But you do not have to have a specific temperature when you're taking this data. As long as you know what the temperature is, you could take this data at 180, 120, 60. As long as you know what the fluid is and what the temperature is, you can get the density, and then you can convert delta P over to head.
Thanks, sir. Let me get this one pulled up. Do you still have to plot the system characteristics if you measure all the piping, fitting, etc. to determine your head? In which case, you could just use delta T and electronic flow meter.
Well, delta T and electronic flow meter is going to be thermal testing. That was what we covered last month. But, let me put it to you this way. The procedure we talked about today is a on-site actual physical test. It's going to pick up all the nuances of that circuit. In theory, if you know exactly what's in that circuit, every pipe length, every fitting, every valve, every component, and you can look up or use a computer simulation to put together the total head loss of the circuit at a given flow rate. In theory, no, you don't have to do this test. But as I was describing, where theory becomes problematic is when you don't know what's in the circuit, or you're unwilling to go, maybe you don't want to crawl back through that crawl space and see if there's another 8 elbows back there or something else that you can't see. This test procedure will pick up the effect of that. If you're doing a purely theoretical one and you didn't realize that, there were another 6 elbows back there, you're missing that effect. So the simulation results are only as good as the data that you're feeding into the simulation. So either one is possible, theoretical. Let me go back to this. This is a theoretical analysis of the circuit. There's no way this software goes to a job site and looks at the piping. If you have to tell it based on what you've seen and recorded at a job site, this is what's in the circuit. And then, yes, it can do a theoretical analysis of that circuit. But there's pros and cons to both. Obviously, this would be very useful in a design situation, in new construction, or you're designing a new system. Now you could say what's in the system. Okay. At least you can approximate as close as possible. That circuit has 125 feet of 3/4 inch pipe. The other circuit has 200 feet of 1-inch pipe. Whatever the case is, you can feed that data in and you can design a circuit. But the reason we wanted to present the testing procedure is because it's just, quite honestly, it picks up things that the theoretical analysis may or may not pick up. And it also picks up those, I call them the nuances, the things like the sludge that happens to be in the, maybe the plug is in a valve somewhere, or the fittings you don't see, or whatever. it picks that up because you're physically testing the circuit and then applying this concept of pump curve and circuit head loss curve intersection to evaluate what a given circulator will do in that circuit.
Hey, John, the person that posted that question actually just posted a follow-up to that question. They said, my follow-up to my question is, now that I plot the characteristics, how do I pick the correct circulator based on all the information I now have?
Okay, well, that kind of goes back to what is the expectation of the circuit. A common way to do it is to say, all right, my circuit, I want my circuit to deliver so many BTUs per hour. I'm going to pick a number, 40,000 BTUs per hour. Okay. That's, you've done the the heat loss analysis of the portion of the building that this circuit serves, and you've determined under design load, I need 40,000 BTUs per hour. The next step is to pick, and this is somewhat arbitrary, but you want to pick the temperature drop the circuit will operate at under design load conditions. And I will stress to you, the common number that is used is 20 degrees Fahrenheit at design load conditions. Now, after I've said that, I'm going to tell you there's nothing sacrosanct about 20 degrees Fahrenheit. If you want that circuit to operate at a 15-degree temperature drop, you can make that happen. It's going to require a higher flow rate. If you want that circuit to operate at a 10-degree temperature drop at design load, excuse me, you can make that happen. So you have to pick, and you might be thinking, well, how do I know? How will I pick it? I'll give you a couple examples. Radiant floor heating in a residential application where you're likely to have people walking around barefooted or in socks, I would suggest nothing more than a 15-degree temperature drop at design load. And if it's a high-end project, I'd probably say 10-degree Fahrenheit temperature drop. Why do I pick those numbers? Because I don't want somebody to say, how come the floor is noticeably warmer over here versus somewhere else in the same room? The larger the temperature drop, the more noticeable that variation in floor surface temperature is going to be. Now, let's say it's a highway garage. People are walking around in, work boots. They're not going to pick up, they're very likely not going to pick up that there's a 15-degree temperature drop from one point in the room to another point in the room versus a 10-degree drop. That's very hard to do, especially with boots on. How about if you're working with radiant panels? Panel radiators or air convectors. Now I can work with 20, possibly even a 25-degree temperature drop. All right. So in any case, we know the heat that the circuit has to deliver in BTUs per hour. We know we're going to pick a temperature drop at design load. And basically, if it's water, I'll give you the approximation. You take the heat loss in BTUs per hour, you divide by the flow rate that you're trying to get the flow. You divide by the delta T at design load, and then you divide by 500 for water. Yeah. So I'll pick the numbers. 40,000 BTUs per hour. We're going to pick a 10-degree delta T. So 40,000, we divide it by 10, we're at 4,000. We divide that by 500 for water. That tells us we need 8 gallons per minute. That's our target flow rate. That's where we'd like it to be. Now, we go back to our pump curves. Let's say we were trying to get 8 gallons per minute. Well, I don't need 22 gallons a minute. I certainly don't need that big pump. Looks like if I pick this pump right here, 8, UP 15100, that you can see if this curve represented the circuit head loss curve, and that's the pump curve, they intersect just about in 8 gallons a minute. That would be one possible circulator. This is going to be a little too small because I'm going to be at about 6 gallons per minute. If I pick the next curve up, I'm going to be at a little over 12 gallons a minute. That's a little higher. It's, significantly higher. Maybe I go to a different manufacturer set of curves. Okay. It obviously depends what hardware do you want to work with here. But that's the procedure. know how much heat the circuit has to deliver, pick a delta T, a circuit temperature drop at design load. If you know the fluid is water, you can divide by 500. If it's antifreeze, there's other factors. Antifreeze is not as good as water moving heat. I'll give you an example. If it's a 50% propylene glycol, instead of dividing by 500, you divide by 450. That will give you the flow rate that you're targeting. And then you go to your pump curves and your system curve, and you try to find a circulator. If anything, maybe just a little bit higher than your target, maybe 10% oversizing would be fine. And that's it in a nutshell.
Okay, thanks, John. Why don't you go ahead and let them know what's going on next month?
Yeah, let's see. So next month we got a topic again. I'm pretty passionate about this topic. We're going to compare air to water heat pumps like the AV systems from Enertech to ductless mini splits. Ductless mini splits are products. Obviously, they're ubiquitous. They're everywhere today. You can find all kinds of manufacturers. You can buy them on Amazon. You can buy them on eBay. They're everywhere. But like any HVAC option, they have strengths and they have limitations. And one of the things that I hear just in talking with contractors, talking with engineers, talking with architects, so forth, gee, I can put in a ductless mini split system for less money than an air to water heat pump system. Is that true? We're gonna look at a system next month, and what we're going to do, just to give you a little preview, we're gonna look at a system that supplies space heating, cooling, domestic hot water, and heat recovery ventilation. Why do I pick all four of those? Because modern homes need all those. Imagine you're constructing a very energy efficient new home. Obviously, if it's, if it's in just about any location in the US, or obviously in the North, you need space heating. Most people that are spending the money to build a new home are going to want cooling. Most people that want to take a shower, wash their hands, or wash dishes, they need domestic hot water. And then the fourth one that I think is becoming more and more of a necessity as opposed to an option is heat recovery ventilation. If you're building a very tight building envelope, you need a certain amount of fresh air just to control moisture, to control odors and so forth in the building. So what we're going to do is we're going to compare how would we provide those four functions: space heating, cooling, domestic water heating, and heat recovery ventilation. How would we do that with a ductless mini split system versus how would we do that with an air to water heat pump system like the Enertech Advantage system? And I think you'll be surprised by some things, and particularly the costs. I'm going to say both are in the same price range, and I've contacted people to get pricing on things to give you an idea. I'm not just picking arbitrary numbers. So we're going to build out a cost estimate for both approaches. But I also want to talk about what does the air to water approach give you in terms of benefits that aren't necessarily present with a ductless mini split. Okay, so that'll be coming up August 21st. Definitely, I'd encourage you to register for that. And then down the road, I'm not going to give you specifics, but we're planning out for the fall season. We're looking at bringing in some guest people, very notable people that I'm sure many of you have heard of. I'm not going to give you the names, but we look forward to having some guests in to talk about how will heat pumps and hydronics, how will those two technologies intersect as we go forward. So looking forward to the fall webinars, and stay tuned. You'll be getting notices on dates and topics and speakers on that.
Yep. Thanks, John. Thanks for the sneak peek. And thank you guys all for joining us. Couple quick reminders. Don't forget to sit tight just for a moment to help us fill out that survey. And then again, you'll be receiving an email in the coming days. It's going to have the Q&A, presentation slides, copy of this video, and a link to register for the next month's webinar. But we hope this was beneficial for you guys and that you will join us again next month. Have a great rest of your day. See you guys.
Thank you, guys.